topic is NGR circuit designed for a 4.2 kV/480 volts 12 pulse 500 kilovolt-amps transformer. The specified let-through current is 15 amps, and the load is a 12 pulse AC volts FD volt C. The discussion revolves around the neutral grounding resistor circuit on the secondary side of the transformer. A common setup involves 2 times 120 ohms resistors connected in a T configuration. One resistor is connected to the zigzag derived neutral from the delta secondary and the other to the Y secondary neutral. The ends of these resistors are tied together and connected to a 277 ohms resistor that is then bonded to the frame ground, achieving a 1 amp let-through in the event of a voltage fault. Directly bonding individual NGR circuits from each secondary to frame ground can lead to circulating currents through the frame. If the T resistor network isn't of a high enough resistance, circulating current can damage the zigzag winding on the delta secondary. Firstly, deviating from the 15 amp specification by delivering a system with only 1 amp let-through is not recommended. While it's tempting to use a value that is known to work, this approach significantly deviates from the specified 15 amps requirement. This deviation may not provide adequate protection in the event of a fault. Secondly, floating the delta and using an NGR on the Y secondary only is another consideration. Floating the delta primary allows the secondary to shift phase with respect to the primary. This phase shift can induce circulating currents within the transformer itself, potentially leading to overheating. Bolting one leg of the delta to ground in this configuration may introduce an imbalance in the system, causing further complications. Thirdly, if the delta primary is bolted to ground, a fault current component would indeed flow through the NGR on the Y secondary. However, the magnitude of this current might not be sufficient for reliable relaying. The current strength depends on the system's impedance and the fault's precise location. It is advisable to use a T resistor network that adheres to the specified 15 amps let-through current. This approach meets the specified requirement and ensures adequate protection. The values of the T resistors should be carefully calculated to precisely limit the let-through current to the specified 15 amps. Another recommendation is to consider using a solidly grounded delta primary. This configuration eliminates circulating currents and provides a stable reference point for the secondary side. Solid grounding also facilitates reliable relaying by providing a clear and predictable fault current path. Ensure the transformer is protected against overcurrent and differential faults. Adequate overcurrent protection safeguards against excessive current draw, while differential protection detects internal faults within the transformer windings. It is very important to verify that the grounding system is designed properly to handle the expected fault currents and prevent potential hazards. The grounding system must be capable of safely conducting fault currents back to the source, minimizing the risk of electrical shock and equipment damage. Properly coordinate the relays with the NGR and overcurrent protection devices. This coordination ensures the proper isolation of faults, minimizing downtime and preventing cascading failures. Relay coordination involves setting the operating characteristics of the relays to selectively trip and isolate only the faulted portion of the system, while leaving the rest of the system operational. When calculating the T resistor values for the NGR, consider the system voltage, the desired let-through current of 15 amps, and the impedance of the transformer and connected equipment. The resistors should be sized to limit the fault current to the specified level while also providing adequate sensitivity for fault detection. When considering a solidly grounded delta primary, ensure that the grounding impedance is appropriately sized to limit the ground fault current to a safe level. Too much ground fault current can cause damage to equipment, while too little can reduce the sensitivity of ground fault protection. When implementing overcurrent protection, consider using inverse time overcurrent relays. These relays provide faster tripping times for higher fault currents, which helps to minimize equipment damage. When coordinating relays, use time current curves to ensure that the relays trip in the correct sequence. The relay closest to the fault should trip first, followed by the upstream relays. This helps to isolate the fault and prevent cascading failures. In addition to the T resistor network, consider using a zigzag transformer for neutral grounding. A zigzag transformer provides a low impedance path for ground fault currents, which helps to improve the sensitivity of ground fault protection. When using a zigzag transformer, ensure that it is properly sized to handle the expected fault currents. The zigzag transformer should also be protected against overcurrent and differential faults. When selecting NGR resistors, choose resistors that are designed for continuous duty and can withstand the high fault currents. The resistors should also be properly ventilated to prevent overheating. Regularly inspect the NGR resistors for signs of damage or deterioration. Replace the resistors if they are damaged or worn. When designing the grounding system, consider using a ground grid to provide a low impedance path for ground fault currents. A ground grid consists of a network of interconnected conductors that are buried in the earth. The ground grid should be bonded to all metallic equipment in the area. Regularly inspect the ground grid for signs of corrosion or damage. Repair or replace any damaged portions of the ground grid. When installing grounding conductors, use the correct size and type of conductor. The grounding conductor should be sized to carry the maximum fault current. The grounding conductor should also be protected against physical damage. Regularly inspect the grounding conductors for signs of corrosion or damage. Repair or replace any damaged grounding conductors. When connecting grounding conductors to equipment, use proper grounding connectors. The grounding connectors should be properly tightened to ensure a good electrical connection. Regularly inspect the grounding connectors for signs of corrosion or looseness. Tighten or replace any loose or corroded grounding connectors. When installing equipment, ensure that it is properly grounded before energizing it. Verify that the grounding conductors are properly connected and that the grounding system is functioning correctly. Regularly test the grounding system to ensure that it is functioning properly. Use a ground impedance tester to measure the impedance of the grounding system. Take steps to correct any deficiencies in the grounding system. Ensure the NGR is sized based on the transformer kilovolt-amps rating and the system voltage. The continuous current rating of the NGR should be sufficient to handle any unbalanced load currents that may flow through the neutral. Select an NGR with a suitable short-time current rating to withstand the maximum fault current for the specified duration. Verify that the NGR resistance value provides the desired level of ground fault current limitation. A lower resistance value will result in a higher ground fault current, while a higher resistance value will limit the ground fault current to a lower level. Consider the impact of the NGR on the sensitivity of ground fault protection. A higher resistance value may reduce the sensitivity of ground fault protection, making it more difficult to detect low-level ground faults. Account for the tolerance of the NGR resistance value. The actual resistance value may vary slightly from the nominal value, which can affect the ground fault current limitation. Provide adequate ventilation for the NGR to prevent overheating. The NGR should be installed in a well-ventilated location, and the ventilation openings should not be obstructed. Protect the NGR from moisture and corrosion. The NGR should be installed in a dry location, and the enclosure should be corrosion resistant. Install the NGR in accordance with the manufacturer's instructions and all applicable codes and standards. Properly label the NGR to identify its function and rating. Provide adequate access to the NGR for inspection and maintenance. Consider using a ground fault relay to detect ground faults and trip the circuit breaker. The ground fault relay should be coordinated with the NGR to provide selective tripping. Periodically test the NGR to verify its proper operation. The test should include measuring the resistance value and verifying the short-time current rating. Keep records of all inspections, tests, and maintenance performed on the NGR. When designing the NGR circuit, consider the use of a surge arrestor to protect the NGR from voltage surges. The surge arrestor should be sized to withstand the maximum expected voltage surge. Install the surge arrestor in accordance with the manufacturer's instructions and all applicable codes and standards. Inspect the surge arrestor periodically for signs of damage or deterioration. Replace the surge arrestor if it is damaged or worn. When selecting the NGR resistor material, consider the temperature coefficient of resistance. The temperature coefficient of resistance is the change in resistance per degree Celsius. Choose a resistor material with a low temperature coefficient of resistance to minimize the change in resistance with temperature. Consider the use of a current transformer to monitor the ground fault current. The current transformer should be installed on the NGR conductor and connected to a ground fault relay or metering device. The current transformer should be sized to accurately measure the ground fault current. Consider the use of a voltage transformer to monitor the neutral to ground voltage. The voltage transformer should be connected between the neutral point and ground. The voltage transformer should be sized to accurately measure the neutral to ground voltage. When designing the NGR circuit, consider the impact of harmonic currents. Harmonic currents can flow through the NGR and cause it to overheat. If harmonic currents are present, consider using a harmonic filter to reduce the harmonic currents. Consider the use of a grounding transformer to provide a neutral point for grounding. The grounding transformer should be sized to handle the maximum ground fault current. Consider the use of a reactor in series with the NGR to limit the ground fault current. The reactor should be sized to provide the desired level of ground fault current limitation. Firstly, consider the National Electrical Code requirements for grounding. The National Electrical Code provides detailed requirements for grounding electrical systems. Ensure that the NGR circuit complies with all applicable National Electrical Code requirements. Secondly, consider the Institute of Electrical and Electronics Engineers standards for grounding. The Institute of Electrical and Electronics Engineers standards provide guidance on the design and installation of grounding systems. Consider using the Institute of Electrical and Electronics Engineers standards when designing the NGR circuit. Thirdly, consider the local codes and standards for grounding. Local codes and standards may have additional requirements for grounding electrical systems. Ensure that the NGR circuit complies with all applicable local codes and standards. When selecting an NGR, verify that it is certified by a recognized testing laboratory. A certified NGR has been tested and found to meet applicable safety standards. Ensure that all grounding connections are clean and tight. Loose or corroded grounding connections can increase the impedance of the grounding system and reduce its effectiveness. Regularly inspect grounding connections and tighten or clean them as needed. Use a calibrated ground resistance tester to measure the resistance of the grounding system. The ground resistance should be low enough to ensure that fault currents can flow back to the source without causing excessive voltage rise. Periodically test the ground fault protection system to ensure that it is functioning properly. The test should include injecting a simulated ground fault current and verifying that the ground fault relay trips the circuit breaker. Keep accurate records of all grounding system inspections, tests, and maintenance. These records can be used to track the performance of the grounding system and identify any potential problems. Consult with a qualified electrical engineer for assistance with designing and installing the NGR circuit. An electrical engineer can help ensure that the NGR circuit is properly designed and installed to meet the specific needs of the application. Remember to consider all of these factors when designing an NGR circuit. The final design should provide adequate protection against ground faults while also complying with all applicable codes and standards. Ensure that the NGR can withstand the environmental conditions in which it will be installed. If the NGR is installed in a corrosive environment, choose a corrosion-resistant enclosure. If the NGR is installed in an area with high vibration, choose a vibration-resistant NGR. Properly coordinate the overcurrent protection devices with the NGR to ensure selective tripping. Selective tripping means that only the circuit breaker closest to the fault will trip, minimizing the disruption to the rest of the system. Use time current curves to coordinate the overcurrent protection devices. The time current curve should be designed so that the circuit breaker closest to the fault will trip before any of the upstream circuit breakers. Consider using zone selective interlocking to improve the coordination of the overcurrent protection devices. Zone selective interlocking allows the circuit breakers to communicate with each other and coordinate their tripping times. Use a ground fault relay with adjustable settings. The adjustable settings allow you to fine-tune the ground fault protection to meet the specific needs of the application. Set the ground fault relay to trip at the lowest possible current level that will not cause nuisance tripping. Nuisance tripping is when the ground fault relay trips unnecessarily, causing a disruption to the system. Consider using a dual-element ground fault relay. A dual-element ground fault relay has two separate tripping elements, one for high-impedance faults and one for low-impedance faults. This can improve the sensitivity and selectivity of the ground fault protection. Use a surge arrestor to protect the NGR from voltage surges. Voltage surges can damage the NGR and other equipment in the system. The surge arrestor should be sized to withstand the maximum expected voltage surge. Install the surge arrestor as close as possible to the NGR. Keep the leads between the surge arrestor and the NGR as short as possible. Use shielded cable for all connections to the NGR. Shielded cable helps to reduce the amount of electromagnetic interference. Ground the shield of the shielded cable at both ends. Use a dedicated grounding conductor for the NGR. The dedicated grounding conductor should be sized to carry the maximum fault current. Do not use the neutral conductor as the grounding conductor. Regularly inspect the NGR for signs of damage or deterioration. Replace the NGR if it is damaged or worn. Keep the NGR clean and free from debris. Debris can reduce the cooling efficiency of the NGR and cause it to overheat. Follow the manufacturer's instructions for installation, operation, and maintenance of the NGR. Consult with a qualified electrical engineer for assistance with any questions or problems related to the NGR.